Okay, kids, it's me again. We're gonna wrap up this nuclear chem in 2 Zooms. We're gonna do number 59 through 67, and then there'll be another Zoom for the rest. This is a photograph of me last Friday, Sunday afternoon now. I was up there cleaning up the room. I had to have a mask on. My mask made from an old pillowcase. Made it and sewed it myself. And it wasn't fun being at the school. It was not fun. I miss you. I hope you're okay. I really do. And I hope if you need anything, you'll have the sense to call me and I'll see what I can do to help you. All right, here we go. These are going to be called radioactive decay problems. And in order to do them, we have to make a T-chart. This is kind of a real life situation, although in real life, they wouldn't use 2 grams. This is a math problem. But in reality, if you have a thyroid problem, thyroid's in your neck, the thyroid gland absorbs iodine, and it uses that to make thyroxine and other hormones to keep your body normal and regulated metabolically. And if it doesn't work, if you're really tired or you're really gaining weight or losing weight, maybe your thyroid's not working correctly, often they will inject you with a little tiny bit of radioactive iodine, and they take a special picture of your neck in a few hours. And depends on how much radioactive iodine shows up in your thyroid gland, they know if it's working or not. And although radioactively it's not good, there's very little put in. And even though it's bad for you, it's better than having to cut you open and look at your thyroid gland. So this is a real thing. It actually happened to my sister. I injected her with the radioactive iodine. But this is an easy math problem, so we use nice round numbers, 2 grams. The question is, if the doctor injects you with radioactive iodine, how long until you have just 0.125 grams left? How do we do that? So at the beginning, you start out with 2 grams times 0. After 1 half-life, you're down to 1 gram, right? It transmutes, half of it changes in the amount of time called a half-life. In 2 half-lives, it's cut in half again. So you started with 2, it goes to 1 gram. In another half-life, you're down to a half a gram. In another half-life, you're down to 1/4 of a gram, 0.250, we're almost there. And finally, after 4 half-lives, you can see clearly on this chart, start with 2, it goes to 1, to a half, to 0.250, to 0.125. The answer is literally right here on the T-chart. It takes 4 half-lives. How long is that? Well, you have to look up on table N what would be the half-life of radioactive iodine 131. And it turns out it's just a little over 8 days, 8.07 days. So if it's 4 half-lives, 4 times 8.07 days is, the math's a little funky there. Radioactive iodine, 0.8021. I don't know where that 0.807 came from, 807. It's 8021 is the correct in red at the bottom. So it would take about 32 days for it to be down to that amount. In this problem, radioactive iron, you put 400 grams of it in your pocket. It's about the size of a baseball. How long until there's just 12.5 grams left? And also, there's another question here. What did the other 387.5 grams become? What did the iron transmute into? First, we'll work on the time, and then we'll work on the decay reaction. After 1 half-life, there's only 200 grams. We need to get down to 12.5, so we're not done yet. After 2 half-lives, we're down to 100 grams, half of a half. After 3 half-lives, half of a half of a half. After 3 half-lives, you only have 50 grams of this stuff left. We got to get down to 12.5, though, so we're not quite done. After 4 half-lives, we're down to just 25 grams. It's going to take 5 half-lives to be down to 12.5 grams. How long does this take? Well, on table N, the half-life for iron 53 is 8.5 minutes. So 8.5 minutes times 5 half-lives is about the length of a class at Vestal, 42.6 minutes. So you start out with 400 grams, a baseball, a rock, a big chunk of metal, iron. And in 42.5 minutes, it's just 12.5 grams of iron. What did the other 387 grams become? What did it turn into? Well, we have to do the second part of this problem, which is called the radioactive decay equation. And that's there on the bottom. The radioactive iron-53 emits a positron particle. How did I know that? I looked that up right over here. And iron emits a positron particle. Positron is 0, positive 1 E. And across the bottom, we do the math on the top. 53 equals 0 plus 53. And on the bottom, it's 26 protons equals 1 plus 25. And the atom with 25 protons is called manganese. So iron 53, radioactive iron 53, transmutes by positron decay into manganese 53. Now, this is, I think this is an Regents question. If a scientist purifies 1.0 grams of radium-226, which is radioactive, how many years must pass till only half a gram of the original radium remains unchanged? So if you start with 1, how long does it take to get half a gram? This is actually a pretty easy question. The half-life must pass, 1 whole half-life to go from 1 gram to a half gram. So literally, you just look it up. Radium has a half-life of 1,599 years. Question 62. What fraction of radioactive strontium would remain unchanged after 58 years? This is definitely a T-chart problem. You got to set up a T-chart. And in this case, we're going to start out with at time 0 the whole amount, 1 over 1. In 1 half-life, we'd be having a half. 2 half-lives, we'd have a quarter. 3 half-lives, we'd be down to an eighth. So look, after the start, we start with 1 and a 1, a whole. In 1 half-life, which happens to be 29.1 years, we'd have half left. After 58.2 years, which is the length of 2 half-lives, we'd only have a quarter. 1 quarter would be left, and 3 quarters would have changed. There's another old Regents problem. What is the half-life and the decay mode of radon-222? How could you possibly know? You couldn't know this. You have to look it up and put your finger in the box. Radon-222, it undergoes alpha decay, and the half-life is 3.823 days. So we need alpha decay and 3.823 days. How could this be a problem? It's got to be C. That's the answer. What is the half-life? Now, this one's a little trickier. Sodium-25 is not even on table N, but that doesn't matter. This is an easy question, and you can figure this out. What is the half-life of sodium-25 if 1 gram of a 16-gram sample of sodium remains unchanged after 237 seconds? We're going to have to make up a T-chart. At time 0, we have all of it, 16 grams. After 1 half-life, we're down to 8 grams. After 2 half-lives, we're down to 4 grams. After 3 half-lives, we're down to 2 grams. After 4 half-lives, we're down to 1 gram. And so it's 4 half-lives. And if 4 half-lives takes 237 seconds, it's going to be 237 divided by 4. It's going to be 59.3 seconds. Okay. New zooms. We're going to do a little bit more, and then we're going to stop. Artificial transmutation. We're going to look at what's artificial. What we've seen before is called natural transmutation. It just happens. And then we're going to get into fission and fusion. How does the sun work? How does a nuclear power plant work? How do nuclear bombs work? And also, what is radioactive carbon dating? And finally, the uses of nuclear elements in medicine. So we're only going to do up to 67. These are quick review. These are going to be 3 natural transmutations. Uranium-238 is on table N. It's going to emit an alpha particle. And when it does that, it will transmute into thorium-234. You can do the math very easy. On the top, 238 equals 4 plus X. X has to be 234. On the bottom, 92 equals 2 plus X. X has to be 90. The element that's number 90 is called thorium. This next one is radioactive hydrogen, and that one is also on table N right here. radioactive hydrogen is going to emit a beta particle. And when it does that, and we do the math, it's going to form into something called helium-3. Now, helium that we're familiar with, that we have in balloons in our lives, is usually helium-4. Radioactive helium is not good to have, but this is what happens. Radioactive hydrogen will transmute into helium-3, and it will do so by giving off a beta particle. The next one, neon-19. Neon is usually a mass of 20. This is a radioactive helium. It's going to undergo what's called positron decay. It's going to emit a positron particle, and it's going to turn into fluorine-19, which is actually not radioactive. Now, these three reactions, black, blue, and red, are all called natural transmutation. Number 65, helium. I'm sorry, number 65 does not give off helium. It gives off an alpha particle. 66 gives off a beta particle. And 67 gives off a positron particle. These are the three basic natural transmutations. And it's simple, right? We've done this math 20 times already. It's not very tough. Now, artificial transmutation is caused by a human being. It's forced. It does not occur naturally, which is good because it usually involves a nuclear explosion. So we're glad this doesn't just happen anytime naturally. It doesn't happen naturally. The first artificial transmutations were carried out by some of the regular people in our class. Remember Ernest Rutherford, my hero from the gold foil experiment, and some other people which we'll get to see. In this reaction, nitrogen-14 plus an alpha particle. Now, you can't just add an alpha particle. Basically, what you do is you get yourself a balloon or a tank full of nitrogen gas. So this is nitrogen normal, nitrogen-14. And then you get a lead box containing a radioactive element that gives off alpha particles, and you shoot them. You literally just shoot them at the gas and hope after a while that one of these alpha particles is going to hit one of these nitrogen nuclei and connect. And when that happens, it's going to form something new called oxygen-17, and a proton is going to be released. Now, the thing in the bottom, it says in black, the thing here that you need to see, the radioisotope is not alone in the front. Nitrogen-14 plus an alpha particle. And that means it didn't just happen. That means you did it. A scientist shot an alpha particle at this nitrogen. It doesn't just happen. This is artificial transmutation. All of the other transmutations that we've seen, we write the radioisotope symbol with an arrow. This becomes. Here, we have a radioisotope plus something that a scientist shot at these nuclei of these atoms. And in this case, you can see that the nitrogen and the alpha particle make something called oxygen-17, and a proton pops out. James Chadwick, who discovered the neutron actually, he took beryllium, which is a metal, beryllium-9, and he shot alpha particles at that to see, well, what would happen if we shoot alpha particles at this metal? And by hook or by crook, because he's really smart, he figured this out, turns into good old-fashioned carbon-12. That's a normal carbon, not radioactive, and a neutron pops out. In this case, what this means, alpha particles get blasted into beryllium atoms. They artificially transmute the beryllium into carbon-12, and a neutron pops out. This is also important. You do not have to know what would happen. You just have to be able to say, hey, does the math work? And let's do this math really quick, because honestly, it's so simple. You'd be like, oh yeah, I should have seen that coming. 9 plus 4, that equals 13. Ooh, I don't like that number. And that equals 12 plus 1. So the numbers on top work. And how about the numbers on the bottom? We have 4 and 2. That equals what? 6. And on the other side, we have 6 plus, of course, 0. So the numbers work. The math is simple. You will not have to be, you'll never be given a problem, beryllium plus an alpha particle, what does it become? It's not going to happen. This is just to show you that this actually is possible and that it does happen. All right? Marie Curie and Pierre Curie, the Curies, they win the Nobel Prize. And she discovers radium. She's the woman that gave Rutherford the polonium to shoot alpha particles. She had alpha particles before he did. She shot alpha particles at aluminum to see what happened. And they were the people that developed or discovered or produced the first artificially created radioactive element. The other ones, they made elements, they were fine, carbon-12 and oxygen-17, perfectly not radioactive. This one is going to form something called radioactive phosphorus-30. So an aluminum bombarded by helium nuclei or an alpha particle gets smashed into it, it turns itself into phosphorus, and a neutron has to pop out to keep the math even. This is called artificial transmutation. You know it's artificial because the front is bombarded with something else. It's not just an isotope that becomes. We're going to stop here.